hear me?
Good. Yes.
All right. Okay. So today's lecture is pretty much the last lecture of mechanics as standard mechanics. And again, I want to emphasize that I'm talking about mechanics not because I want you to learn mechanics as it is. I mean, in fact, standard mechanics is just, it's a huge science. And there are some departments, like in Moscow University, mathematics department is called mathematics and mechanics. So about half of the people there are doing mechanics, some sort of like, and there are a lot of structures there. I was trying to show that there is different reformulations of the mechanics, and in fact the Hamiltonian reformulation is probably the richest one of them, and it has very beautiful geometrical structure, and people are still working on those things, and they still try to understand what different things mean. And so it's not, it wasn't the purpose of this lecture to actually teach you mechanics as it is. I mean, I hope I did tell you something which you didn't know before. But what I'm trying to do is to illustrate different ideas which are common in physics in all other areas of physics, and but they can be illustrated very simply on mechanical systems, something which you actually have some intuition about, and you can think about what happens without, like, you know, all that full-blown math or whatever. It's all the simple things, and they actually can be understood quite straightforwardly. So today, what I'm going to talk about is another extension of oscillator physics, and as I try to explain to you that oscillators are our major tool to understanding everything else, in fact, and everything else is the first step you do for any other science, including, I don't know, quantum field theory or whatever. You convert that problem in a collection of oscillators first, and then on top of that you understand it first and that bunch of oscillators, and then you try to build on top of what you learn. But there are some other things which are actually quite surprising in oscillator itself. So a typical oscillator can, without dissipation, so for today I will talk about a little bit about dissipative effects at the end, but for now it's just an oscillator without dissipation. Very simple, right? It's with a minus sign here and x here, right? So this is an oscillator. There's literally, it's probably the simplest possible thing you can do. I mean, well, you can do trivial things like having force which does not depend on coordinate. But this is the first extension over the trivial thing, over the completely trivial problems. Now what I want, and that's it. We know the solution. It's the thing is oscillating with its own natural frequency omega naught, right? And that the example of it is just a mass on a spring, a pendulum which makes very, very small oscillations around its equilibrium, or as I tried to explain last lecture, it's pretty much everything else. If it is in equilibrium, when you come to a system, it's in equilibrium, then you disturb it a little bit. If that disturbance is small, then it will behave as an oscillator, right? And so that's basically a starting point for all of them. Now you can have some extension on it. You can have many couple oscillators which are which sort of induce itself. Like, so you can try to solve this kind of problems when you have two masses and two springs and so forth. It's actually trivial, not trivial, but it's a simple extension of the same equation. It just will require, because it's a linear equation, then everything is just converted into linear algebra, and then we know a lot about linear algebra, all the determinants, you know, the permutations, eigenvalues, and so forth. So in particular, those frequencies are called eigenfrequencies because they're a solution of some eigenvalue equations in linear algebra. And by the way, eigen in German means own. Its own. So what it means is that it is its own frequency. That frequency is a property of an oscillator. It's not a property just of the motion, right? For any potential, you remember that for potential of arbitrary forms, there are some energies at which the particle will oscillate, and it will have some frequency of oscillations. But that frequency, in generally, will depend on the amplitude of the oscillations, and it means that the frequency is a property of that particular motion. It will depend on the initial condition, on the energy. Remember that we had that for more problems. But in this particular case, when you have harmonic oscillator, the frequency is just a property of the oscillator itself, and it doesn't depend on how we set up the motion. And that's exactly why we can use it as clocks. So we don't have to worry about the initial conditions. It will always be like that. So everything is known, everything is fine. But now I want to extend that problem a little bit, and I say that the parameters of the oscillators of my oscillator, like you remember that omega naught is a parameter of oscillator now, right? And it depends on the mass and then the spring constant. In case of oscillator, it depends on the acceleration of free fall g and the length of the pendulum and so forth. And in electric circuit, it depends on L and C. And it can be computed. We know how it is. But now let's imagine that some of those parameters depend on time, right? So if you want, you have a pendulum and you change its length. You change its length with time, right? So you sit in there and pulling it a little bit.
Did you try that?
Oops. Doesn't mean. Sorry, my iPad starts to talk to me. I'm going crazy. So it's parameters. Sorry. Parameters of the oscillator depend on frequency, like the length of the pendulum, or the strength of the spring constant or mass depends on time. You do something to a system all the time. Then there is some trick. I mean, it's a little bit more complicated than what I'm trying to present, but there is a trick to convert the equation when parameters depend on time. Exactly, it's the same equation, but now your frequency depends on time. So the frequency now is a function of time. And we want now to consider this equation. Now it's obvious that the solution of that equation, and of course now we need to know the initial conditions and so forth. So we have x of t equals 0 equals x naught, and v of t equals 0 equals v naught, right? They supplied somehow, and on the later times, the dynamics of the system is governed by this equation with a known function omega naught of t. That's the function is something which you do to the oscillator, so you have complete control over it, and you can set up whatever function you want. And you want to know what kind of properties of that oscillator will have. Now, that question by itself, I mean, it's still a linear equation, but now the coefficients depend on time, and the solutions are much more complicated than just the simple oscillator. You cannot write anymore that the solution of this equation equals I don't know, amplitude times sine omega naught, now function of t, right, times t plus phi. This is incorrect. You cannot do that, because now if you differentiate that function, you will have to differentiate this function omega naught of t also, and it will get out of the equation, and you will have all the derivatives of omega naught also in the equation. So it will not work for sure. Right? So you have to solve this equation in U, and now it's a second order differential equation with coefficient depending on time, and there is no simple solutions of that. You cannot assume that the solution is just sine or cosine, because it's not now time translation invariant. It becomes a complicated equation, although still linear. So all the properties of linear equations, like sum of the solution is also a solution, will still work here, and the solution is still have one constant, which is the common amplitude. and so forth. So we know some of that, but in each case that has to be solved specifically. And there is a huge theory of that second order differential equations, linear differential equations with coefficients depending on time, and there are some classifications of those equations and all of that, and majority of the solutions are given by some special functions like hypergeometric function or whatnot. And it's again, there are lots of things unknown, but in general, I mean, you have to solve it all the time again. Again, you know this function, and you always can solve this equation numerically. You know initial conditions, you know this function, so you just calculate it step by step, and you will know the solution. There is no magic there, but so it is not what we want, though. What we want, especially as a scientist, we don't really care about any particular case. And as I said, in any particular case, you just take a computer and solve it numerically. And not a big deal. Everything is well defined. All the theorems of mathematics tell you that the solution exists, it's unique, and so forth. So you just then solve it by computer. What we want is to find out some sort of features. What kind of things can we expect? What kind of new phenomena can we expect? And if we find some new phenomena which we discovered in this situation, we want to figure out then how to use it, and if they're useful or just some academic interest on without any use, which is also good, and so forth. So we want to understand some general behaviors of the system. And in order to do that, we need to sort of restrict our problem, because it's sort of clear, because that function is now completely arbitrary. It's something which you do to a system. So you can have a lot of different solutions for different functions and so forth. So there is no chance to get some universal and some general properties here. So we need to some sort of restrict that function. And the first restriction is that we say that function does not change very much. So it is pretty much a constant, and there is some time dependence on top of that constant. But the function is never going to become too large or too small, right? Because if it becomes too small, then eventually you get just a free motion. And if it becomes too large, then eventually that becomes just a major term, and you just look at the asymptotics and so forth. So you want it to be some sort of keeping omega naught almost constant, but still changing with time. Right? That makes sense? That's the setup of the problem. Because guys, one of the things which is important for in science is not how you solve the problem and how you set up the problem. The setting up the problem, a problem is actually the major work. After you set up a problem, you give it to a graduate student, and that's how science is done. And then the graduate students then solve them. They're good at it. And so the setting up of the problem is the most interesting and the most important part of it, because you really, when you're setting up the problem, you really have to understand very well what you want from it, and that's a creative part of all these problems. So here we want to consider a situation when our frequency almost constant but changes with time a little bit. So that's one thing, and the second thing is that actually would be very interesting to know if the situation when this function is changing periodically with time. Right? So it means that there is a special period. So that function omega, if I try to draw it here, right? This function this is time, and this is my function omega naught squared, a function of t. This function which is sitting here. So if I want to know this, what I really want to do is to say that this function is also periodic with time, right? So it's something around omega naught squared, like I don't know, average, whatever. It goes around some constant and it changes periodically with time, right? So then this function will have its own period. This is t, and that period, let's call it tp, right? And then you can say that that function itself has its own frequency. So this is frequency. Let's call it omega p. P is for pumping, and it's equals to 2 pi divided by the period at which it changes. Okay. So why is it interesting? Is because after the period, the tp, the equation turns into itself. Right? If I take this function and I add to time that tp, right, that period at which it changes, the full equation becomes the same equations again, and so forth. It becomes the same equation all the time. So I always return my system back to where it was. Does that make sense?
Yes. Yeah.
But the solution doesn't have to return back to where it was. Right? So after some time, you start with some initial condition. After some time tp, the system returns back to where it was, but the initial condition at this point of time will not be the same as this one. So the solution will change all the time. But there should be some sort of rules how it changes with time. And that's exactly what's interesting. And then it becomes sort of, you can look for some structure of different states.
You know a physical example like that?
Yeah, I will show it. Moreover, I will show you a device which does that. But I will also tell you that you actually know it also. Right. Yeah. So that's actually how mathematicians approach it. So what it is called is transfer matrix, and it's how initial condition at this point transferred into this point, and then you can consider the property of the matrix, how that vector x naught v naught changes with after every period tp, and then exploring that matrix, you actually, the properties of that matrix, you can tell a lot about what's going on there. And that's exactly the mathematician's approach to such problem. Okay, but it's too much. I will use it, but I will never develop that mathematics. It becomes a little bit trickier and involved. It's one of the most complicated problem in standard mechanics class. But I tell you what the results are, and I will try to say why it is plausible and how you know that it is correct. All right, but before I do the mathematics, I still need to understand some sort of scales which I have in the problem. So there are two frequency scales or two time scales. There is this time scale tp, right? And there is, you remember that the frequency is pretty much constant, right? It shakes a little bit, but it stays almost constant. So what it means is that oscillator almost has the same its own frequency, right? So I can set up another time scale, which is the period of oscillations of this oscillator, which is just t equals 2 pi divided by that omega naught, like in some sort of average, right? Like that. And if that amplitude of that shaking of omega naught is not large, then it doesn't really matter how to average it, so it actually makes sense. So I have two time scales, right? And those time scales does not have to be related with each other. Remember that this time scale is sort of time scale of the oscillator itself, and this time scale, the pumping time scale, is what you do to a system, right? So you can either shake it very quickly or shake it very slowly, or shake it at the frequency which is sort of the same as its natural frequency, right? So there are three cases, and those cases are, let's say that it's omega p is much larger. This time is much larger than omega naught, and No, let me first write the other way. So this is omega p is much smaller than omega naught, so I shake it very, very slowly. I just slowly change the parameters of my oscillator. Another one is when omega p is much larger than omega naught. And the third one is omega p is of the order of omega naught. And it can be like factor of 3, 5, whatever, but it's still sort of the same order. Okay? That makes sense?
I'm still unsure of the difference between TP and T.
Right.
Could you go over that one more time?
Okay. So forget about the dependence on time. Right? So as I said, that I'm considering that function omega naught of squared of t to have very small amplitude. Right?
Okay.
So omega is almost the same. It's staying almost constant. It's just on the top of the constant you have a little shake. Right? So let's then we can assume that in first approximation, zeroth approximation, we forget about the dependence on time here, and then it's just a standard oscillator, and that standard oscillator has its own frequency omega naught and its own time period.
Okay.
Oscillator going on. Now TP is the period with which that function omega naught squared of t is changing. So you're sitting there on an oscillator and you change its parameters. And you change it periodically, but the period at which you change, I mean, it's with your own hands, it can be completely arbitrary. So that's exactly the TP, that the time during which you change that parameter.
Okay. I think that makes sense.
Yeah, so you can think about it if you want, if it's easier for you, about that electric circuit like LC oscillator, right? It oscillates on its own, right, with some frequency, and now you're sitting there and changing its capacitance, for example, periodically, right? Like you tune in your radio, back and forth, back and forth. And you can do it with any time scale you want. You can do it with any period you want. You can do it slowly or you can do it faster. Right? And that's exactly that period. But the natural frequency of your oscillator is this period. Okay?
Thank you.
And so those are two time scales, and the relationship between them is what you do to the oscillator. So it can be any kind of relationship. And in particular, you can change your oscillator very, very slowly. Right? So that omega p is then very small, and very small. You can compare only things with the same dimensionality, right? You cannot compare cucumbers to tomatoes. So it's so you can change it very slowly. Very slowly, it means that omega p is very small in comparison to omega naught. The frequency of the oscillator itself. Or you can change it much faster than the frequency of the oscillator. Or you can change your change and the frequency of your change and the frequency of the oscillator can be of the same order. Right? And that's more or less, of course, there is some boundary cases where you go like, well, it's on the same order, but it's already a factor of 20, right, between them. So is it this one or this one or what? Well, there are some cases where you really, I mean, you have to solve it on computer, and it's but on those cases we can use those small those relationships between those two time scales, two frequencies, in order to simplify the problem. Remember, we always want to simplify the problem and see what are the general features there. All right, so if the setup of the problem is clear.
Yeah. Yes, it is.
All right. Yes. Now, what I'm going to do now, I'm not going to solve any general equations here or anything like that. Don't worry about it. It's actually quite complicated story about what to do like exactly. What I want to do is to describe some examples of those, and to show that on those particular examples there can be some features which are very universal and has extension to quantum mechanics and so forth, and they're very and they're actually very useful, in fact. So I will start with this one, and in this one, so I want to give you an example of such system, and that example is well, usually what when that lectures are in normal classroom, I just show it because we have a Foucault pendulum in the next building. I'm in the rectangular physics building, and there is also around. It's called Mitchell Institute of Physics building, and there is a Foucault pendulum, that huge pendulum on the center of that building. Have you seen it?
Yes. Yes.
So if you've ever been to that building, you cannot miss it. It's the biggest thing there. It's a huge pendulum which goes like what is it, 6 stories with the rope, and there's a big, massive sphere on the bottom, and it goes back and forth all the time, right? And so there is some motor on top of it which keeps it going back and forth, and I will discuss it a little later how that motor works. And but nevertheless, you can consider it, you can forget about that motor and consider it just to be in a normal pendulum. Any questions? All right. So you have this pendulum now. And there seems it seems like nothing is changing there. I mean, parameters are not changing for that pendulum, but it's actually not quite correct. But the change of the parameters is not visible to an observer when you observe it, because it is related to the fact that the Earth is rotating. You know that our Earth is spinning, right? You know that our Earth is sphere, right? And it's spinning around some axis. And so what it means is that that pendulum, which is here and right in the next building, it's actually traveling around the circle, right? You understand this, right?
Yes.
Yes.
Now, when it's traveling around the circle, it's the vector of gravitational force is actually changing direction, right? It's always going to the center, but you now travel around, right?
Yes.
So the value of G is not changing. The absolute value of G is not changing, but its direction is changing. And what it means is actually it becomes a non-trivial problem how to figure out what happens to oscillator to that pendulum when that G is changing its direction. And there must be something. I mean, it's the G is not a constant in time. Remember that constant means constant vector means that its magnitude and direction is not changing. But now the direction is changing. So what it's even more complicated because we are sitting on the same frame of references as the pendulum. So in our frame of references, G is constant, right? It's going right down all the time. But the story is that my frame of references, in which both I, an observer, and the pendulum are, it's not inertial frame of references because we ourselves are moving around the circle. And when you move around the circle, you have acceleration. So we are not in the inertial frame of references, and we are observing that pendulum, which is also in the same frame of references, which is not inertial. So there are some effects which come in from there, and that effects are very small, right? It's not a big deal. And the first thing what you would think about is to completely disregard them, and you will figure out that the pendulum is just oscillating with its own frequency and everything's fine, and it's correct, right? But the story is now is that the effects are small, but they work all the time. So that small effect should be multiplied by a long time. And whether now you have a very small number multiplied by the large number. And when you do that, when it is a small number, large number, normal number is actually not known, right? You have to do the calculations to figure out how the product is working. And if you do that, what you will find is quite an interesting story, and it's actually the essence of the Foucault pendulum. So let me explain you what happens if you never heard about it before. So here is our latitude. It's called, right? I could never remember which one of them is which. Right. So we are sitting right here, and my pendulum. So my pendulum is oscillating this way. Right. So if I am observing this pendulum, there one parameter of the pendulum which we always disregarded in all our studies, and with me, or probably with some other in your mechanics class. So the pendulum is oscillating in one particular plane, right? So it's if I draw a pendulum this way, we assume that it's actually oscillating this in the plane of the blackboard, right?
Yes. Yes.
But it doesn't have to, right? I mean, the pendulum can oscillate in any other plane. And from point of view of pendulum, that doesn't matter. For pendulum doesn't know what you call a blackboard, right? So it will oscillate in whatever initial in whatever plane you start initially the oscillations, right? So what actually happens in this case? That now that plane of rotation is just a plane which goes through the center of Earth and just sitting there. So what actually happens when the pendulum is traveling, right? The Earth is rotating, so the pendulum is traveling along this line. That plane of oscillations will start to rotate. Okay, so when it goes back exactly where it was, so my change of parameters gone through exactly the period of the change. What will happen if this was its initial plane of oscillations, right? Then when it comes back here, that plane of oscillations will not be the same. It's actually will be some twist between them. Okay. So again, that's probably it's not a big deal to solve such problem. It can be done, and the result is the following: that this rotation of the plane, that phi, that angle phi, which is rotation of the plane of oscillations, equals to the solid angle which the path is making. Right, so that path along which that oscillator is traveling, right? It sort of cuts a little cap out of our Earth. And if you now look at the solid angle here, omega, then that angle phi will be equal to the omega. Right? Does that make sense?
Yeah.
So that's the result of the. I mean, it's not something which I invented. Well, first of all, it was not me, and second, it can be calculated. It really can be, but again, I don't want to throw too much math at this place. So what? But what's interesting is that the rotation of the Earth doesn't matter in this case. The fact that it's rotating. What matters is that if you take a pendulum and you travel, and imagine that Earth is not rotating, and you travel with that pendulum around the closed path, like that. Then when you come back, that the plane of oscillations will again change its angle, right? And that angle again will be just the solid angle of the cone, which doesn't matter what the path is. It doesn't have to be circle. It can be anything, but it will have a solid angle, and the change of the when you come back, the plane of oscillations will rotate in the angle which equals to the solid angle of your path, right? So what it means now, if you look at this. By the way, I always say that when you return back, that angle will be changing. Remember that we discussed that story before when we talked about curved spaces. Then in curved spaces, the angle between this vector and this vector doesn't make sense. The only vectors which have angles which you can talk about angle between them is that when the two vectors are going from the same point. Then around this point in very small vicinity of this point, your space is flat, and then you can talk about angles. Otherwise, it doesn't matter. You have to do some constructions in order to say what is the angle between this vector and this vector. They do exist. It's called Lie dragging and so forth. But it's constructions of top of everything. So that's why here I'm just saying I always compare the two planes in the same point when the pendulum returned back to the same point. So the story is the following. In case of rotating Earth, it's actually very easy, right? I set up a pendulum. I draw a line on the floor, right, along along the plane where the pendulum is oscillating, and then I just wait one day, right, and I come back after one day, and I will see that the plane, the oscillator now is oscillating on a different plane, and then I can measure this angle. And if I can measure this angle, I will know that the solid angle of the path which the pendulum does, but that solid angle actually depends on latitude, right? It's called latitude, right? That angle of of where I am. I can actually figure out what my coordinates on Earth. Well, one of the coordinates by this procedure. All right. So that's now. If you think about this now, there is no physics involved in the answer. It doesn't matter what kind of Earth we have. What is the G vector? What is L of the oscillator? Nothing is involved. It's just a solid angle of the path, the rotation of the plane of oscillations. So it's only geometrical. It has all of this. The answer is only geometrical. It has only geometrical properties of the path which I'm taking in order to come back. Right? Does that make sense? That's what answer tells you. But it also, but that means that it's very, very general and universal result. Because it now doesn't depend on anything. The answer is just a geometrical property of the path. So it means that it should be completely universal property of such systems, and it indeed is, and it can be shown that it's geometrical. Just write in the equations of motion and see that what you're doing is just some geometrical properties of the path which you're taking. And moreover, it also means that it's probably not constrained to mechanics itself, only to mechanics. It should be the same in every other situations like that for any other problem, and it indeed is. And in fact, the fact that it's a geometrical property, the Foucault pendulum was known a long time before, and people computed it, and everything was fine. But the fact that it's geometrical property was understood only later on. It was understood actually in I wrote it somewhere. Just a second. Yeah, it was understood only on 1985. Right? 1985 is when I was in high school. It's yesterday, right? So it's and moreover, it's actually quite an interesting story that in classical mechanics, that fact that it's a geometrical property that you measure in just geometrical thing, and it must be universal for all mechanical systems was understood after it was discovered in quantum mechanics. In quantum mechanics, that kind of phase, which actually that phi, the rotation of the oscillator is the phase of the oscillator, and the phase of wave function, and that it's called in quantum mechanics Berry phase. And the beauty of it is that it doesn't depend on details of your system. You can have whatever system you do, but then in some parametrical space you move your system back where it was through some path, and then you can compute how your solution what the phase of the solution changed during that motion. And it's completely universal in a sense that it doesn't matter what kind of system you have, what kind of Hamiltonian you have. So what it means also is that you don't need to know the Hamiltonian precisely. You don't need to have precise description of your system in order to make some predictions. And those predictions actually do have some physical consequences. We can measure those things. So you can predict the results of the measurements without actually knowing much about the system. It's enough to know that it has some non-trivial path in some parametric space. So that's why those things are so powerful, because it's impossible to know everything about the system. We of course say that that particular system can be described by this Hamiltonian, this, but in reality, when we do so, we disregard a lot of details, and it's never known whether those details are important or not. You have to do what you do usually. You take your system, you simplify it, you write some in case of quantum mechanics, it is always Hamiltonian. You write the Hamiltonian of the system, then you make some predictions, and then you have to check what everything which you thrown away when you wrote the Hamiltonian, when you simplify the system. Will they change the prediction or not? And if they change, how much? If the change is observable or not? So those always have a lot of research, and a lot of answers then comes out like, well, it probably don't. That's pretty much a good answer. And but in this case, in case of that, if we have an experiment which measures just that sort of rotation of the plane of oscillations, we actually know precisely what it is, and we can make very precise predictions. And they're so precise that one of the most precise things which we actually can measure in contemporary physics are coming from the physics which is very similar to this one. So it means it allows you to do something with the system, to understand something about the system which you actually don't know too much about. Okay, because it has just geometrical property. It does not depend on the physical system. So and this is the prime example of those kind of things in standard mechanics. Now, as I said, in quantum mechanics, that is called this phase is called Berry phase. In classical mechanics, it's called Henny angle. Henny is the name of the guy who discovered it, and Berry phase was discovered in 84, and that guy in classical mechanics sort of discovered it in 85. So 1 year. He actually knew about the Berry phase in quantum mechanics. Then the guy was smart enough to say that, well, if it's quantum mechanics, it must be the same in classical. And then he sort of constructed the whole theory of those kind of geometrical terms in classical mechanics. And people now use them a lot, because again, they allow you to think about some pumps or some sort of it's all electrical electronic pumps, some sort of electronic structures or whatever which uses those phases, and then we actually know exactly what will happen. Okay, does that make sense?
Yes.
Yeah.
So what I'm trying to emphasize here is that although it's just a simple mechanical system, but observing it and trying to understand it completely actually leads to a lot of very, very good progress. And in fact, if you ever think about, if you ever try to check what people are doing, say in condensed matter, then about half of all the papers now they're talking about like topological insulators, Kitaev models, and stuff like that. And they all have sort of origin from that kind of phases. Because it turns out that for very complicated system, we still can say something very interesting and even do something which is what people try to call a quantum computer. And for quantum computer, again, you must have stability of your system. Very, 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 it must be very, very stable. And typically systems are not. There are always dissipation, the system is coupled to the environment and so forth. But if the things which you want to measure depends only on those geometrical phases, then those details are not important. And you have very, very stable situations. And then you can do some quantum computing on using those kind of constructions. So that's the route which people try to take, because without it, the coupling to environment pretty much kills everything when you try to do quantum computing in a standard way. All right, so that's about this case when I change my my parameters very slowly, and that's exactly the case, right? Although that pendulum is huge, it takes about a second if the period is about a second, right? But the period of change of my position is 1 day, right? So although it's sort of slow motion of the pendulum, it's still that the change of the parameters are much slower, right? So it's exactly what that inequality gives us, demands from us. All right, so that's one case. So now let's move to a different to the next case, this one, and see if something can happen in something interesting can happen here. And now if I didn't use the answer, but I don't know the answer, but if I didn't know the answer, then I would say that nothing interesting can change here, can be here, simply because what's happening? You have an oscillator and you shake it real fast, right? That's what it means. But it's already shaking very fast because there is a bunch of atoms which are like hitting it all the time. All right, so it's already, and some of them get stuck, so the mass is changing and then goes back and so forth, right? So what could be different here? It's not really something which not already been done to the systems. So in this sense, it shouldn't be very anything spectacular shouldn't happen here, and that would be wrong actually. And but it's in the case, and this is that actually exactly correct if you have just this equation. Then you can average this equation over that very fast shaking, and then show that that averaging can be done correctly, can be done here, and then what you have is this. It's just a separate motion, because it's a linear equation. You will have some sort of separate motion, very fast shaking of your system, and small oscillations with and slow oscillations with a given frequency. Well, the frequency can change a little bit, but that's due to averaging, but it's okay. So it's but the story becomes a little bit actually a lot more involved when you have a non-linear oscillation. So when you have a pendulum. Like you remember that pendulum is linear oscillator when the amplitude of oscillations is very small, but nevertheless there are some nonlinear corrections. You remember the real for a pendulum, the real equation is phi double dot equals minus omega naught squared times sine phi, right? When phi is very small, we substitute instead of sine phi, we substitute phi. But in reality, there is some other terms here, and then the next one is phi to the cube, and so forth. It's a Taylor expansion around zero, and those terms are sort of corrections. And when we discuss just an oscillator, it's just a pendulum. They're not very important, and we can compute the corrections and say that they're not important. But when I shake it, that corrections, nonlinear corrections, becomes very important. Because those exactly the terms that they couple, they don't allow me to separate the motion into small shakes and slow motion. They will couple those two motions together, right? You cannot. They're not linear equation. When the equation is not linear, the sum of solution is not a solution anymore. So that nonlinearity becomes important, and if you include that nonlinearity and that shape, then actually miracles can happen. I'm serious. It's forget Harry Potter. That's it. It's a miracle. So the problem which I want to show you is this one. So let's imagine that we have a pendulum, and it has some length L, and it has mass M. Well, mass doesn't matter. It's on Earth. And what I do now, I take this pivot point and I shake it up and down like this. Okay. So what then? So I say that the position of that pivot point is described by some function like psi of t. It's the position of this where I go, how much above and below some point I go. And what I demand now is that this function was very fast, very small. The amplitude of the shake is very, very small, but it is very, very fast. Okay. Now I can tell you exactly how fast and how small they should be, and then write all this story because I know how to solve this problem. But let's forget about it. The intuition is good enough. It's a small amplitude, but very, very fast shaking. Okay, does that make sense?
Yes.
The setup of the problem. So now the question is, what will happen? And in order to answer this question, we need to understand what kind of answer do we want. And let me explain to what I mean. What I mean is the following. Let's imagine. Well, I don't need to imagine it. Let's imagine you can. My son goes to a movie, right? And then he comes back and asks him how was the movie, and his answer usually it was okay, and that's it, right? It's not very many details about the movie, right? In this answer, but he always does that, and you probably do that to your parents too. I definitely did to mine. But nevertheless, but what do I expect really from that question? How was the movie? I definitely don't expect him to describe me frame by frame, right, of the movie. So I do expect him to lose some details and to tell me something essential about the movie. Right? That's a typical conversation. And now social adjusted people know what kind of details I expected, and I'm not a very social adjusted person, so my answer is always it was okay. But because there is no real boundary, you really cannot pinpoint the boundary where what level of details are expected, right? You have to be social adjusted for that. I don't know how to do that. And but nevertheless, in any case, you will always leave some of the details of that of what happened outside of the conversation, right? You cannot describe all the details. But there are other examples when it's more clear what kind of details you don't want there should be included. Like if you're taking a trip from here to Houston and somebody asks you how was the trip, right? You can say okay, that's what I do. But more social adjusted people would say that like, oh, it was good. I mean, the weather was good, the view was good. Oh, it was not good, whatever. Just say something. We saw some courses, whatever. But no one in their right mind will describe all the bumps on the road. Although when you travel, right, you're not traveling. It's not completely flat road. You always have some bumps on some places, right? You go up and down. But no one will ever describe those things when you talk about your trip. Well, you can say that it was bumpy, but that's it. You will not say that like at 1 hour and 50 minutes and 23 seconds there was a bump. In 25 seconds there was a bump. It's boring, right? And it's completely understood that kind of details is definitely don't matter. And the reason for that is that because there's a huge time scale differences. Those bumps happen very, very, very often, very quickly, right? And you typically describe something which happens on a time scale on how you view on the windows is changing, right? You move from one place to another, the view from the window is changing, right? And during that time when it's changing, there were very, very, very many bumps, right? And you don't describe those bumps, you describe that view which you see. Right, so it is clear that you have to do when you need to do that, even for non-social adjustable person by myself, because of the very, very clear distinctions of the time scales. There is slow processes, how the view is changing, and very fast process, how like the car is shaking. And I know in this situation that I need to discard fast one and look only on the slow and describe only the slow motion, right? So this separation of the time scales is actually very, very important and very powerful tool in physics. If you think about it, that everything which we describe ever about physics, you always disregard some fast motions, right? If you throw a ball, right, the ball when it flies, it sort of changes shape and so forth. But that's very fast changes. And it's on comparison to that fast changes, that motion of the ball is very slow. So you completely forget about these fast changes and you describe only the slow motion of the ball itself, and that's what you call the motion of the ball itself. Right? Now, if you look at water, right, it's like you're sitting on the next to the river, right, and it's flowing next to you, and so you never think about it that it's actually a bunch of atoms or molecules in the water which actually jiggle around very quickly, back and forth, right? That's not what you see. That's not what you describe. You describe the motion of the water as a whole. But that motion of the water as a whole is a result of that very, very quick motions of all the atoms. And yet you can write, you can describe the motion of the water itself without referring to the motion of the atoms. Right? And that's what is called hydrodynamics. That science which we write the equations for the water or liquid or gas motion as motion as a whole, disregarding the motion of the atoms, single atoms. So what we do, we sort of average out the fast motions and think about it as a slow motion of the water itself. Does that make sense?
Yes. Yeah.
Yeah, so pretty much for every physical process, what you do, you average over very fast motions, or we call it average out, or sometimes we call it integrate out. It's the fast degrees of freedom. And you observe, you pay attention only to the slow degrees of freedom. Those slow degrees of freedom can be quite fast on human scale, but they still much slower than those shakes of the atoms in the water, right? So there is a huge separation of the time scales of what we are interested in and what is really happening. And when there is a huge separation of the time scale, we know where to put the boundary. It's somewhere in between, so that we disregard all the fast motion and on the slow motion, and we look only on the slow motion. Right? That's a completely natural and normal thing to do, but it turns out that it's a very, very powerful tool to do that. And that's exactly what needs to be done here. What we want disregard those shakes and only observe the pendulum itself, how it's moving. If you want to, if it's not clear to you, then just imagine that your eyesight is not good, like my own, right? In order to do that, to disregard very, very small and fast motions, that's very small and fast, right? All I need to do is to take off my glasses. And then I do not see that small shakes. But I will still see that motion of the pendulum. And then I can ask, how do I describe that motion of the pendulum? Does that make sense?
Yes.
All right. So I actually have the pendulum with the shake, and I'm going to show it to you. And I have this device. So I need, in order to do that, I need to lower my camera because the device is staying on my table here. So don't get dizzy. And okay, and like this. Do you see it?
Yes.
Yes.
So it's made of Lego, and it was actually where I teach that I solve this problem during lectures when I teach. I was teaching the graduate analytical mechanics, the graduate class, and I was showing the problem. And I told them in class that I wish I had the device to show it. And the very next day, a guy, one of the students, brought me that device made of Lego. It's beautiful. I mean, it's the simplest possible way to do that, and it works beautifully. So, what is this device? It has a pendulum. Let me stay so that I can watch. Actually, it is here. This is a pendulum. Do you see it?
Yes.
Yes.
So it's going down, sitting down, and when I turn that crank here, right? It's going up and down. Like this. Do you see this?
Yeah.
Yeah. And I can do it slowly, or I can do it fast. So let me do it fast. That's what we see. Here you go. Do you see it?
Yeah.
Yeah, do you see that it's standing up, right? And it's actually stable. You see that sometimes it's moving a little bit off, and then it returns back. Right?
Mm-hmm.
So let me show it again. I love this thing. Here we go. It's quite an interesting. When some visitors from some physics departments came to my office, I always show that device to them, and everyone is absolutely amazed. I mean, it's unbelievable. It's a real nerdy toy. So let me see if I get it right. There you go. And like this. All right, that's good.
Yes.
All right.
Yeah.
So that's the toy. That's the device which I have, right? And it does exactly what is described here. Now it has some additional feature. You see that when the pendulum is the lowest point, the pendulum actually hits the platform here, and that you see that it hits it right there. It's again, the student invented it on its own. It's because otherwise I would have to have the third hand to put it up. The up position is stable, but the down position is also stable. So when it hits the platform, it just goes up and then oscillates there. That's what it is for. Just because I have only two hands, unfortunately. And so it's but otherwise it's exactly the same story, and it has exactly the same. It's exactly the physics which I want to describe. So apparently, if I start to shake it now, and I sort of I don't see it anymore because I shake it very fast and very small amplitude, that pendulum will acquire a new stable position. It has a stable position right on here, right? Always, that's always a stable position. But it will also acquire. Like let me write it. Let me draw it here. So here's where my pendulum can be. That's the circle, right? It's a circle. It has a stable position down here, but if I shake it fast enough for a given amplitude, that should be the smallest amplitude, the faster I need to shake it, it will also acquire the stable position here. And it also means because stable, unstable, stable, unstable should go after one another, there will be two more unstable positions somewhere here and here. Right? And then that pendulum can actually oscillate somewhere in between here, in between the unstable positions. Okay. And again, that happens because I shake that pendulum, and that little motion is coupled to the slow motion through those nonlinear terms in the pendulum. And then if I average out over those fast motions here, then it turns out that my effective potential energy in which that pendulum is now slowly moving actually is changing, and it requires some additional minimum on top, right? And then it oscillates on top. So it looks like for the case of the pendulum that gravity has changed sign, right? It's sort of starting to point out. Of course, it is not so, but it's for all practical purposes. That's how it looks like for the pen. Now, it actually has some consequences. That story, and in particular, if you you know that when they build that MKS, I think that's the station on which it goes on orbit around the Earth, like out there. And they wanted to do some experiments in zero gravity there, because there is no gravity, it's weightless. And they built some laboratories there, and of course, when you're there, you need to pump air in whatever you build, because there is no air out there. And in order to do that, you need to set up some pumps. And the pumps were set up in such a way that they actually, the laboratory was vibrating just a little bit, but very fast. And it turns out that it completely screws all the experiments, because from the point of view of the experiment, that looks like a gravity. After you average out all the little shakes, it looks like there is a gravity in your system. And so they had to rebuild it and move the pumps out of the building and do something to eliminate vibrations. So it does have some consequences. But what is important, even more important than MKS kind of things, is that those small vibrations actually change the effective potential energy which the pendulum sees. So when I average out of those oscillations, those fast motion, the averaged potential energy which that pendulum sees in its motion is actually different than what it was before. And it's so different that it can require a new equilibrium position, right? And that's exactly what is happening, like in situations like phase transitions, like magnetic phase transition, when you lower the temperature and then the material becomes ferromagnet, it acquires a magnetic moment at some temperature. That's actually exactly what is happening there. That your atoms are shaken so hard there that their shaking is translated into effective free energy of your magnetization. And then after, when you lower the temperature, that free energy acquires a new equilibrium position, and then your magnetization is happening. So it's prime. This is one of the examples which you can do to say that how fast degrees of freedom can affect the motion of the slow degrees of freedom. Okay, and it's, by the way, the story how that new minimum appears is exactly universal. You remember that it was the maximum before, right? So if I now try to in this region try to draw what is my function here is, then it was what is my potential energy. So this is phi, this is potential energy, right? So when I shake it not fast enough, what I have is a maximum, like this, right? But when I start to shaking it fast enough, then what will happen is the story, exactly the story which we have before. So you see that it's an inverted picture with respect to what we studied last lecture, right? And then you see that this maximum becomes a minimum here, and two new maxima appears, right?
Yeah.
And again,
Yes.
if it is so, it must be described by the fact that your potential energy has quadratic term and term of the fourth order in phi, and then what and then the sign of the coefficient in front of the quadratic. So you have something like this, right? And the sign of this coefficient changes when you shake it fast enough, and then maximum becomes minimum at the center, and then you have a new stable position. Okay, so it's exactly the same story. in the sense that it's a very, very universal feature. And it can be looked at in different ways. Any questions? Come on, guys. Any questions? Is anyone out there? Oh, yes, at least one person here. All right. So, I mean, but think about it. Well, the most interesting part of that story, in my opinion, is how surprising it is. Really, I mean, it's you just start to shake it, and you don't think that any much will happen, but it's a very drastic change. All of a sudden, your pendulum starts to oscillate like on top, very unnatural, right? So it means that you have to build a completely new intuition about to know how that integration of the fast degrees of freedom affecting your the motion of the slow degrees of freedom. And it means that there also can be some stuff which we haven't discovered yet, or we haven't found uses yet, because we don't have that intuition. And if you don't have that intuition, you don't use it in making some other machines, right? And maybe we will lose some good opportunities. Yeah. All right. So that's this story when I have very fast shaking. And now I want to go to the last one and talk about when that period of change of the parameters is about the same frequency as the natural frequency of the oscillator itself. Now I want to tell you first that first of all, you all know that you have been using this kind of parametric oscillators since you were probably 2 or 3 years old, or 4, I don't know. All right, and here's the story. It's a pendulum, as usual, right? But let's call this pendulum a swing. And now there is a person sitting on this, staying on the swing. It is staying because I don't know how to draw a sitting person. And when you do this, you can move up and down, right? And then you can swing for more and more.
Yes.
Right? Have you done that?
Yes.
Yes.
Good. So, but that's exactly what it is, right? When you're moving up and down, your center of mass is moving up and down. It means that the effective length of that swing is changing, and it changes periodically. And that means that it's exactly this equation, right? That makes sense?
Yeah.
All right.
Wait, can you repeat that real quick?
Well, when you're moving up and down, right? It means that your mass, your center of mass, is moving up and down on the swing, right? But what is the length? But what is the length of the pendulum? It's a length from this position to the center of mass of that ball, right? So your length is changing a little bit.
Okay, I see. Thank you.
Yeah, but the frequency is function of is what is G divided by L square root, right? So if you change L a little bit, then you change frequency of your oscillator a little bit. And that's exactly what it is. And now, if you think about it, that change of the frequency here, that function, when you're moving just up and down, it's very small, right? So this amplitude of this change in this case is very, very small, right? And you're not going up there. You're just sitting here, and it's. I mean, if you have a large swing, like a couple of meters, like 3 meters, for example, and you're moving your center of mass is just around 10 centimeters, something like that, right? And plus, you are not the only mass on the swing. The swing has its own mass, so its center of mass is actually moving just a little bit, like a few centimeters, up and down. So that frequency change is very, very small. And here it's enough to actually for you to go further and further. Right?
Right.
Yes.
And this is called parametric resonance. Now notice that it's completely different from the normal resonance. Normal resonance is when you have the oscillator, right? X double dot equals minus omega naught squared x plus some force which changes with time, right? And then you have a resonance, and if the frequency of the force is equal to the frequency of omega naught, or it's actually can be twice that or half of the frequency, right? So no, twice the frequency. So you still have that resonance, right? And so you don't have to and that's that situation with that normal frequency. If this is a small kid, right, and there is a parent staying here, and that parent is pushing that swing periodically, right? You don't have to push it every period. You can push it every other period and so forth. But nevertheless, the period of that force must be the same or commensurate with the period of the oscillations, right? That makes sense. So this is a normal resonance when a parent pushes the kid. But when you're sitting there and moving up and down, this is completely different story. There is no external force, right? I'm looking at this pendulum as a whole, and there is no external force acting on it. It's only you moving up and down. And yet it gives you the oscillations which go further and further. That situation is called parametric resonance, and mathematics for it is completely different than the mathematics for this force. And you can see it right straight from the equation. If you have a force acting here, right, then if you start with the initial conditions, x of t equals 0 and v of t equals 0 equals 0, so you just stay put like down there, right? And then parents come in and pushes you. Or, probably in your case, not parents, but friend. Yeah? And pushes you, right? So even with this initial condition, you will still have oscillations. Right?
Yeah.
But in this case, it's completely different story. If my initial conditions are just 0, right? Then you see that x equals 0, x of time, right? X as function of time equals 0 is always a solution of this equation, no matter what. Doesn't matter what the function is. Right? It's 0 equals 0. So this is always a solution, and that solution satisfies the initial conditions when those initial conditions. Right? And that means that this is the solution. Mathematics tells you, mathematicians tell you that equation has a unique solution. If you find one, there is no other. So this equation, this solution satisfies both equations and initial conditions. This is the solution. There is no other solution. Okay? So it means that if you start at 0 position and at 0 velocity, you will not be able to start oscillations by going up and down. Okay?
Okay.
And you know that, of course, because every time you need to do it yourself, what you do, you first push yourself, right? Then you jump on the twin, and then you start to pump it and going up and down. Right?
Right.
Because you know that.
Yes.
What is more surprising is that even little kids know that. A 4-year-old kid would sit on there and will yell, "Mom," or "Pop," my dad in my case, "give me a push." Because that kid is already knowing that this equation has a unique solution. It may not know those words, but it has enough intuition actually to know that. And so he knows that with this initial condition, there is no way for him to start that oscillations. He doesn't use those words either. And so he asked the parent or to whatever, whoever is nearby to give him initial push or her initial push, and so he can continue. All right? Isn't it amazing? I mean, that your intuition actually knows something about those equations, which you then spent like a couple of years studying. All right, so now I will not be able to do that here. It's not enough time, and again it's a little bit technical then to solve it. But for this equation, for that kind of problem, it's exactly the story which somebody suggested at the beginning of the lecture. That what you do, you start with initial conditions here, and you sort of do a transfer of the initial conditions on this period, right? And say that at this point you have this initial conditions times some matrix, and it is matrix because you have two values here. So if you multiply it by matrix, you can consider it as a vector. If you multiply it by matrix, you again have the vector which you call new initial conditions at this point. And then that matrix must be the same all the time because it must depend only on the equation itself. So you can then say that when you go further and further, your matrix is multiplying on itself all the time. And then if that matrix has one of the eigenvalues which is larger than 1, then you will have then you multiply a number which is larger than 1 over and over and over. It's growing, so your amplitude is growing. That I just described the way how to solve this problem mathematically, right? And how this problem can be solved. And it's actually doable. And the properties of that matrix can be figured out on with some generalities. But now but I'll just give you the answer, and the answer is actually drawn on my lecture note, and I'll try to draw it again here. So the condition, this condition for the parametrical resonance is the following: that omega p must be equal. Then I have 2 divided by n, times omega naught. All right, so this is my omega naught, and if I now that n is any natural number 1, 2, 3, 4, 5, and so forth, and if I do that, then at this and I push it with a frequency which satisfies this condition, then I will have a parametric resonance. All right. So now what I want to do here is I say that here I write a graph, and you see that the story is that if I now do the natural thing, I write it this equation of the following way: that n equals 2 times omega naught divided by omega p. Right. So I put omega p down here and n up here. So what I will do, I will use this number as one of the coordinates. So this is omega naught divided by omega p. All right. So when it means that my frequency is when my frequency is growing, omega p is growing, actually moving to 0 in this case. And in this axis, I will write. I will use that the amplitude. How much that omega naught is changing. Okay, does it make sense? So you see that my omega naught is characterized by 2 numbers. One is a period of frequency of how it changes, and the other how much it changes, the amplitude. So that's exactly what I'm doing. I'm putting here this is the frequency but inverted, and here I put the amplitude of the change. So in what I see here is that the first resonance will happen when this value equals 1/2, right? So when this is 1/2, that cancels with this 2, and n equals 1. This is the first number which I have. So that will be the first. The first resonance will be here at 1/2, then the next resonance will be when this ratio equals 1, right? And then you see from here that n equals 2. Then this one will be 3/2, and so forth. Right? So this is the points of the resonance. And now I want to on this space I want to show where the resonance exists. So what turns out is that it's there is some regions like this. No, let me draw it differently. So it's 1/2 here, and then it goes much narrower here, and much even more narrow here, and so forth. I have a much better picture on my lecture notes. So the resonance is happening everywhere here and here, in between those lines. Okay, does that make sense? So if the parameters of your change, you remember that change now is how you move up and down. That moving up and down it has two parameters. It's how often you move up and down, the frequency, and how much you're moving up and down, right? So this is how much you're moving up and down, and here is the frequency of how you move of your motion. So what it tells you is that if your amplitude you're moving up and down a lot, right? Then what you have, then in this case the resonance will be everywhere here. So you don't need to be very precise with your frequency. And what it tells you is that the larger the amplitude of the change of the parameter is, the less precise you need to be with your frequency in order to get the parametric resonance. Every time you are somewhere here, you have a resonance. You're going further and further away. Does that make sense?
Yes.
Right. So that's why it's actually keep an exact timing is hard. So that's why it's much easier to swing on this on the swing, which where you can move up and down much further, right? So it's shorter swing, basically. And when you have very long swing, your motion up and down makes very little difference, and then it's very hard to actually to keep motion in the resonance, because you have to be very precise. But you still can do it. Or you can actually do it on different frequencies, but then you have to be even more precise, and so forth. Right? They become very narrow. Now this is all without dissipation. With dissipation, there is some change, and the change is the following: that you see that those corners go exactly at 0, right? So it means that even you have infinitesimally small amplitude, if you're very precise with your timing, you will still have a resonance. Okay, but it actually changes when you have dissipation. In dissipation, what will happen is those lines get like this, and now the resonance happening over here. So what this graph means is that in order to get the resonance, you need to have some particular frequency, but you also need to have that amplitude larger than some threshold. Otherwise, you will not have a resonance. Okay, is it clear from here?
Yes.
So you see that it's not touching 0, so you have to have some finite amplitude in order to start the resonance. The resonance again happening on those pink areas, and and that's exactly what you do now. Also, that if you have very rusty swing, you really have to push it a lot, go up and down in order to get the resonance. When the swing is perfect, you need only very little work to do to move it up and down. If it's rusty, then you actually have to go to some real good amplitude in order to start the motion, right? So that's something which you again have the ideas of from just simple intuition of spending probably some time on the swings. All right, does that make sense?
Yeah. Yes.
Now there is so that's about the parametric resonance. By the way, it works exactly the same with electronics, and usually that resonance is much more useful than the resonance from the external force. I mean, when you have a filter or something like that, it's external force, it's fine. But if you want, but if you can construct a filter which uses parametric resonance or amplifier which uses parametric resonance, it will be more precise. It will keep everything better. It's those resonance usually stronger than normal ones. So that's one remark. And the other remark is the following: that we'll talk about it, and when we study quantum mechanics, and what is written here for any person who knows quantum mechanics, what is written here is the Schrödinger equation is in the periodic potential. And Schrödinger equation periodic potential, it's the big words, but it's just a description of how quantum mechanically, how an electron moving through the crystal. The crystal is periodic, and it is potential, and the electron is moving through the crystal. So what, and then there are parametric resonances and the dead areas and so forth. And what you see that they are going from one to another, right? And so the area of the parametric resonance in the context of Schrödinger equation is what is called prohibited state. But in between, electron can sort of move. And what it turns out then, that when it is in between, then there is no, that electron actually doesn't know about the lattice. It's moving, its mass changes a little bit when it's moving, but it's moving as if there is no lattice whatsoever, right? So that's why metals conduct electricity. So that's this is, otherwise you cannot understand why when an electron can actually move through the lattice. A lattice is a positively charged ions. Electron is a negatively charged particle. They should like keep him, right? The electron next to themselves. They attract each other very strongly. So if an electron gets around so too close to an atom, the atom would capture it, right? And then it means that there can be no conductivity without quantum mechanics and without that kind of picture. But it turns out that in quantum mechanics, that the story is exactly the same as the parametric resonance, just inverted. And then what you find is that electrons just zipping through that periodic potential through this lattice as if there is nothing there. All right, and that's why they conduct electricity. All right, any questions?
No.
All right, then that's it for today. And the next lecture is on Friday. And see you there. And thanks for coming.
Thank you.